The Overlapping Generations Model, Chapter 3.2 from the book Public Economics. Hello and welcome to this introductory tutorial into Chapter 3 of my book Public Economics. I will introduce you to the Overlapping Generations Model, which is a model from the 50s and 60s devised by Diamond and Samuelson. And this model will help you to analyze the big questions of today, for example, on the demographic transitions, on debt or pensions. Now, in this overlapping generations model, what you consider in this very simple form that we will analyze are two periods. In the first period, people work. Let's say this takes 40 years. And in the next period, they retire and live from the savings or the pensions, which takes up another 40 years. And in each period, we have two cohorts, the young and the old, who are alive. Now, the material is taken from my book, Public Economics, Chapter 3. If you cannot get a hold of a copy, I would like to encourage you to download the teaching material from my homepage, where you can find the slides. This is the first tutorial on Chapter 3. Subsequent tutorials also consider numerical applications. So we look at the dynamics in the overlapping generation models, and in later chapters we study the optimal amount of pension, stuff like this. And therefore, I would encourage you to either get some knowledge of MATLAB or Gauss and upload the upcoming slides, subsequent videos, and learn how to solve these programs numerically. Now let us get into the slides, and I would like you to download them from my homepage. Sorry, I need to get into these slides. So you should have these slides in front of you. Public Economics, the Macroeconomic Perspective, Chapter 3 OLG model. And we look at the first part, the OLG model. So as I mentioned, this model was set up by Diamond and Samuelson independently. And it is important models to study economic problems. So, for example, the issue of pensions and debt, demographics, or family economics. So what is special about this model? So let's compare it to models you might know from your macroeconomics undergraduate and graduate courses. There you have learned about the ISLM model, which basically ignores issues of savings and capital accumulation, which are important in the long run. Next, you might have learned about the Solo model, which looks at capital accumulation and how an economy behaves in the long run as it accumulates more capital and is subject to capital deepening, so that the capital stock per capita increases. But in this model, in the Solo model, savings are exogenous. So you just save a certain portion, certain fraction of your income, let's say 20% of income. In the overlapping generations models, we go one step further. So in the overlapping generation models, savings will be an endogenous function of the interest rate. You might know this from the Ramsey model, where savings are also an endogenous function of the interest rate. But different from the Ramsey model, people have finite life in the overlapping generations model. So they die after a certain amount of time for certain, while they live infinitely in the Ramsey model. And this opens up the possibility to take the Solo model and analyze some questions which the Ramsey model is not amenable to. So in the Solo model, you have different cohorts, young and old, and some old cohorts just live from their pensions and their savings, which is absent from the Ramsey model. So if you want to study a reform of the present pay-as-you-go pensions, where the young people contribute to the pension system, which transfers these contributions to the old, it is important to have the demographic structure and to have young and old people in the model. There you need the solo model, the overlapping generations model as a natural model or framework. Similarly, some questions of national public debt can best be analyzed in the overlapping generations model. So for example, in the Ramsey model, we know that Ricardian equivalence holds. So if a government increases its public debt, what will the households do? Well, they just increase savings because they know in the future taxes will go up because the government has to repay its debt. So all that is the extra spending, extra debt of the government will result in extra savings of the household, and these effects just cancel. So we call it the Ricardian equivalence result, that public debt is neutral. This is different in the overlapping generations model because of the finite lifetime. So if the government takes up a couple of hundred millions, billions of debt today, for example, to pay for the corona crisis, well, I myself know, well, perhaps I don't have to repay it, but the young people have to repay it in 30, 40 years when this debt comes due one day. So here, Ricardian equivalence fails, and public debt will have an effect on economic dynamics, on output, savings, consumption, and so on. Also, the overlapping generations model is the natural framework to study demographics because the two cohorts, the young and the old, well, they do not need to be of equal size. So in the future, we know we have many more old people and fewer young people. Fewer young people have to pay for more old people, and our pension system might collapse. This is the topic of chapter 6 in my book, and we will find out, well, the fiscal policy or the public debt policy of countries like the United States, for example, are still sustainable. So you can pay the pensions for this higher number of retirees in the United States. But in other countries like Italy, Germany, or France, this will not happen. And these countries will get to a threshold in the 30s where the payment of the pensions is no longer feasible with the help of taxes, income taxes, or social security contributions. Another natural question that arises that can be analyzed in the overlapping generations model, of course, are family economics. So, for example, how much child care subsidies should the government distribute, or should you get married? Why is female supply smaller than male labor supply? All these questions can easily be studied in the overlapping generations model, and you will find a lot of applications in my book with regard to these 4 issues: pensions, debt, demographics, and family economics. Now, let us get into the model. As I mentioned, the household lives 2 periods. He's a worker and a retiree. So let's assume at the age of the first 25 years, you just go to school and live with your parents. So economically, you're not that important. Sorry. The next 40 years, people are working until the age of 65. That's period 1. And in period 2, they retire, another 40 periods. So notice that these 2 periods must be of equal length so that it's easy for them to overlap, that we have one worker or one cohort of worker and one cohort of retirees alive at the same time. This is difficult to achieve if the periods were not equal. We start with an easy example. Labor supply is inelastic, so each person just supplies 1 unit of labor. We will look at elastic labor supply in later chapters, but for now, let's start with the very easy case. We have a production function that uses labor and capital, and we assume constant returns to scale. and we consider a decentralized competitive equilibrium. So in this case, if we have constant returns to scale and we have competitive labor and factor and goods markets, you know that equilibrium profits are equal to zero in this economy and that the factor prices, wages, and interest rates are equal to the marginal products of capital and labor, respectively. Now let's get into the demographics. We denote the number of young people by NT, number of people NT in young generation T. And we assume that they grow at the rate n. So each of the young people has 1 plus n children. So equation 1 describes the dynamics of the number of young people. The population growth rate will also be equal to n, and you can see this if you look at total population. Tilde n is equal to the number of young people, nt, born in period t, and the number of old people, which were the young people in the previous period, t minus 1. So you add up nt plus nt minus 1 to get total population, tilde n, and it's easy to show that this also grows at n. So total population and young population and also old population all grow at the common growth rate n. The household supplies 1 unit of labor, so we set labor supply L equal to 1. And when he's old, he does not work anymore. So L2 is equal to 0. The super index denotes the period of the person, whether he's young, period 1, or old, period 2. The subindex T denotes the time period T. Total consumption is simply the consumption of all young and old people in period T. So C1T and C2T are the consumption of the young and old in period T. And we assume that lifetime utility can be presented by an additive utility function. So a sum of instantaneous utility when young, U of C1T, and utility when old, U of C2, T plus 1. And we weigh future utility, old age utility by factor beta. And we have the standard assumption that marginal utility is larger than 0, that it declines, that marginal utility is declining, U double prime equal smaller than 0, and that it approaches infinity for consumption equal to 0. The discount factor beta is just assumed to be larger than 0. Different from the Ramsey model, it must not be smaller than 1 because we have a finite sum of utility here, equation 3. So with the Ramsey model, you add infinite additive terms here. And if beta is larger than 1 in this case, well, then the sum also becomes infinite. And you cannot deduce simple first order conditions. Now, in the overlapping generations model, this is not necessary because we just sum up 2 terms, 2 instantaneous utilities. We assume that the household does not take care of his children, so he does not leave bequests. This will be added later. And that the households earn real wage W. So the savings are equal to total income W minus consumption C1T. And in the second period, we do not receive any pensions or income from working. We just consume all our savings SD. And of course, we get an interest rate on our savings. So look at the timing. We assume that in the first period, period T, we start at the beginning, work, and at the end of the period, we get our wage WT. Now, at this time, we also consume, so at the end of the period, we have savings S. Now in the next period, we start with savings S, and the savings will earn the interest RT plus 1 over the period T plus 1, and at the end of the period T plus 1, we consume C2 T plus 1. And therefore, we can derive our intertemporal budget constraint by substituting equation 4 into equation 5, and we get that our present value of total consumption, C1 plus C2 over 1 plus R, is equal to total income, which is equal to our wage. And we can derive our first order condition, so maximizing lifetime utility, uppercase U, subject, which is equation 3, subject to our intertemporal budget constraint 6, and we derive the first order condition for this maximization problem, so that marginal utility today is equal to beta times 1 plus R times marginal utility tomorrow, so next period. This equation you also know from chapter 2, from the Ramsey model, is called our Euler equation. So it gives you the first order condition if you should save an additional unit of your income or not. If you consume it, if you do not save, you get marginal utility U prime C1, the marginal utility from consumption C1. If you save it, it gives you next period return 1 plus R times this one unit. And you get the marginal utility U prime of C2 next period per unit of good, and you have 1 plus R units. But you discount future utility, next period utility by the factor beta. And of course, in equilibrium, you must be indifferent with regard to the use of this extra unit of savings. Otherwise, you would increase utility. For example, if marginal utility of consumption C1 is larger than the right-hand side of equation 7, well, you reduce your savings and increase your utility. And otherwise, if U prime is smaller than the right-hand side, you increase savings, and this would result in an increase in lifetime income. So this is your first order condition with respect to savings, and you can substitute your budget constraints into this equation 7. So consumption is equal to wages minus savings on the left-hand side, and next period consumption is 1 plus R times savings on the right-hand side of this equation. And this gives you savings as an implicit function of the wages W and the interest rate RT plus 1 in the next period. And this can be illustrated with this with this simple diagram that you know from Macroeconomics 101, which gives you the intertemporal budget constraint as the budget line, the red line, with the intersection point at the abscissor WT, and the slope is 1 minus 1 plus R. And the indifference curve, which is the curve for your lifetime utility to be constant, which is the tangent curve to this budget line, and this results in the optimal point A. Now, the difference between your consumption, between your wage W and your optimal consumption C1 star is your savings, which is the blue line in this diagram. And it's easy to see what happens if your wage increase. So this will shift the budget line outward. And if consumptions in this and next periods are normal goods, which they are due to our assumption on the utility function, this will increase consumption of both C1 and C2. So here we have also an increased savings. Otherwise, consumption in the next period would not go up. So here the increase of wages are anonymously on savings. Higher wages result in higher savings. Now, what happens if the interest rate increases? Now, if the interest rate increases, we can afford higher consumption next period. So our intertemporal budget line rotates around the point WT0 and it rotates clockwise for higher interest rate. Now, as a consequence, we have a new optimal point, optimal intertemporal consumption point. And here, the effect of the interest rate on savings is not clear. And we will argue this in more detailed version next. So we look at the properties of the savings function, which is implicit function of WT and RT plus 1. And we will look at the Euler equation, which I replicate here. Marginal utility of consumption today is equal to beta times 1 plus R times marginal utility tomorrow. The left-hand side is a function of savings, and the right-hand side is a function of savings. And we will study the equilibrium, which is defined by the point of intersection of the left-hand side and the right-hand side. So we graph the left-hand side, which is the marginal utility of consumption this period as a function of savings. And when the savings go up for given wage, this means that our consumption declines, so our marginal utility goes up, so our function increases. We have illustrated the left-hand side as a function of savings. Notice that we have restricted here savings probably to 0, because if savings fall below 0, well, or to 0, then we do not have next period consumption at all. And this would, of course, not be optimal, because then the marginal utility of next period consumption is infinity. And of course, it makes sense to reduce consumption today, save more, and increase consumption in the future. Now, the right-hand side is a function of the savings rate, psi, and it's decreasing. So to notice that the right-hand side of this Euler equation is decreasing function of savings, look at what happens to consumption next period. If savings increase, consumption 1 plus R times S will increase, and therefore marginal utility will decline. And it's easy to show that the point of intersection is unique for all our assumption, and we have a unique equilibrium and a unique savings S prime, S star. Now, what happens if we increase wages? This will not result in a shift of psi. Psi, the location of psi is constant. It's not a function of W at all, as you can see by inspecting the Euler equation, the right-hand side. Now, on the left-hand side, if W goes up, this means for every level of savings that consumption will go up, and therefore marginal utility will decline. So this shifts our curve U prime, our left-hand side, downward. So this is the effect of an increase of the wage from W1 to W2. Our left-hand side, U prime, shifts downward. And as you can see, savings increase anonymously. Higher wages imply higher savings. Now, with regard to the effects of the real interest rate R, this is a little bit more complicated. As you can see, the left-hand side is not affected. R is not contained here on the left-hand side. You don't find it on the left-hand side. With respect to the right-hand side, we have two effects. Because higher interest rates result in higher consumption next period, ceteris paribus, the right-hand side increases. But on the other hand, higher consumption next period also results in lower marginal utility. So the right-hand side decreases. And we cannot say a priori which effects dominates. In fact, these are the substitution and the income fact here. So let's look at an example here. If the interest rate increases from R1 to R2, our curve psi shifts to the right, and higher real interest rates result in higher savings. But this need not be the case if the income effect is very strong. So let's look at what's happening here in more detail. What is the effect of an increase in the interest rate R on the right-hand side psi? So we differentiate the right-hand side of the Euler equation, beta times u prime of 1 plus r times s times 1 plus r with respect to r. So we have to use the product rule on the first term and the second term. And it's easy to derive the derivative of psi with respect to the real interest rate r, which is given by the next to the bottom line on slide 15. So it's beta times u prime of c2 times 1 minus sigma, where sigma is given by this expression in the bottom line, so which is equal to minus double prime u over u prime times c. So sigma is the elasticity of the marginal utility with respect to consumption, or which is also equal to the inverse of the intertemporal elasticity of substitution. So you got to know this intertemporal elasticity of substitution in chapter 2 on the Ramsey model. So the inverse of the intertemporal elasticity of substitution, the intertemporal elasticity of substitution 1 over sigma gives you how the consumption growth rate reacts, the percentage change of the consumption growth with respect to a change in the real interest rate. And depending on whether this value is smaller or larger than 1, you can see that the effect is positive or negative. So let us summarize what we derived so far. We have seen that savings increase with wages anonymously, but that savings only increase with the interest rates if and only if the elasticity of intertemporal substitution is larger than 1, meaning sigma is smaller than 1. So the empirical evidence for sigma points in the direction that sigma is actually larger than 1. So often we find values in the range of 1 to 4. So this implies that here in our simple two-period model with realistic intertemporal elasticities of substitution, savings would go down with higher interest rates. Well, the reason that we do not observe this empirically, usually we observe, well, that savings increase with interest rate, is that we have so far neglected income in the second period. So in chapter 2 in the appendix, I show you in my book that if we have second period income, well, then this result does not hold anymore. So then even for intertemporal elasticities smaller than 1, an increase in interest rate can still result in higher savings. But for the simple model that we look at right now, this result will hold. So let's get into the production side of the economy. So we assume that we have a representative firm, or equally that we have a large number of identical firms, and each is producing to constant returns to scale. So we can use the construct of the aggregate production function YT. Aggregate production is produced with aggregate capital and labor, K and L. And we assume constant returns to scale so that production per effective labor, Y over L, can be expressed as a function of the capital intensity, K over L, so lowercase k. Profits are simply production minus wages minus interest. And if we maximize profits pi with respect to labor and L and capital K, we derive that the marginal product of labor is equal to the wage and the interest rate is equal to the marginal product of capital. Or in our per capita function, smaller case, lowercase f, we can derive the right-hand side of equation 12a and 12b. So I often talk about per capita production when I talk about f. More accurately, it is the production per young worker, because we have normalized the labor supply of each worker to 1 unit. L measures both aggregate labor and the number of workers. So in general equilibrium here, the labor supply, the number of workers, N times labor supply, L, which is equal to 1, is equal to aggregate labor demand, uppercase L. We also have that investment is equal to the increase in the capital stocks, so we neglect any depreciation here. We will consider this later. And investment is equal to aggregate savings. Now, aggregate savings, we have the young people. They each save lowercase s, and we have NT young people. So NTST is savings of the young people. And the capital stock of the previous period, or of this period KT, is owned by the only people that were alive at the end of last period, so the old people. And they just consume the capital stock, disinvest the capital stock, so that the investment is equal to the difference between aggregate savings of the young, NTST, minus this savings of the old KT. So if we substitute investment into equation 14 into equation 13, we get the capital market equilibrium. The aggregate capital stock, uppercase KT plus 1, is equal to aggregate savings. So again, remember the timing in our period. We have a period which starts, period T starts at point 0. Then at the end of the period T, we accumulate, we get our wage, we consume, and we have our savings. Now we take, at the end of the period, we take our savings, and this forms the basis for next period production, and we produce over the next period T plus 1 with the help of the capital stock KT plus 1, which then is repaid again to the old. So this is our capital market equilibrium. Now, if we divide equation 15 by the number of young people NT, we get to equation 16, which describes the dynamics of our economy, our per capita capital lowercase kt plus 1 at the beginning of period T plus 1 times 1 plus the population growth rate n is equal to individual savings ST. And individual savings, as we have just previously derived, is a function of the wage rate WT in period T and the interest rate R T plus 1 in period T plus 1. And since we have constant returns to scale, wages W and interest rate R are just function of the capital intensity lowercase k. So equation 16 is just a dynamic equation in the variables kt and kt plus 1. And we can analyze the dynamics of the model with the help of just one state variable, lowercase k, the capital stock per worker, and this amounts to equation 17 or 18. Now let me show you the result of a numerical example that we consider in the next tutorial. Here you see the dynamics of the capital stock over time. We start with the capital stock in period 0, which I set equal to 0.02, and we substitute it in our dynamic equation here. So on the right-hand side, we just substitute K0 equal to 0.02 and compute capital stock in the next period, in K1. After this, we substitute K1 again to compute K2, and so on. And we iterate over this equation to get the following dynamics. As you can see, after about 5-6 periods, the dynamics, the capital stock has converged to something like a rest point here. It keeps almost constant. And we call this the steady state. So the steady state is the rest point dynamic system might converge to. And two questions naturally arise. Is there a unique steady state? So is there perhaps another steady state up here? And is it stable? So if we have a shock so that the capital stock is higher or lower, for example, after the coronavirus, does the economy converge back to the old steady state? And these two issues are considered under the heading existence and stability. So does there exist a steady state K, so that Kt is constant and equal to the value, which solves equation 17 for constant value of K? And is it stable? And in dynamic systems, so more formally, this is a difference equation, first order difference equation, and certainly nonlinear. Different possibilities arise. So here I graph G of Kt and take three examples, the red line, the green line, and the blue line. They're all examples of a function G of Kt, which gives us next period capital stock. And here the ray from the origin at the 45 degree is the unit line. So this gives Kt plus 1 equal to Kt. So we just mirror the value of Kt from the abscissa to the ordinate to Kt plus 1. Now let's analyze these three cases in turn. We start with the red line. And in this case, if we start with any value K0, the red line gives us K1, the next period value. And K1 is equal to K1 in the next period. So in the next period, we have K1 here. We just have to mirror it at the unit line. And this gives us K2, again, as the value that we can read off from the red line. And K3 again, K4, and so on. And as we can see, in this case, in the red line here, we find that the capital stock converges to 0 in the long run, asymptotically. So 0 is the only steady state. Now let's look at the nice case, the blue line. Let's assume we start with K0, any value of K0, which gives us K1 on the blue line. We mirror it to Kt again, and this gives us K1 and K2 again, as we can read off the blue line, the value of K2 from the blue line. And you can see we converge to B, which is our steady state. In B, if Kt is equal to K, we stay in the point B. And we have shown that it's stable for values of Kt below the steady state. And now let's look at values above the steady state. Well, if we start here, we again converge to the new steady state, so it also converges from above. So in this case, and this is the nice case, we have a steady state, a unique steady state in B, which is stable. Now, C is another case. The green line is the third case that we would like to consider. And here we have three rest points. The origin, when we have no capital stock, we have no production, so we don't consume anything. We can't save anything, so we rest there and die because we cannot consume. Point A, when we are on point A, we do not move away from point A. And point C is another steady state. Now let's look which of the two steady states is which of the steady states of the three steady states origin A and C are stable. Now if we just have a little bit of capital stock, as you can see with the help of the green line, we move into the new steady state A. So the origin is not a stable steady state A, we move into A. If it's a little bit above A, we move, let's say we start at capital stock K0 at this point. This gives us K1, and we move into the point A from above. So A is locally stable. But is it globally stable like point B? No, it is not. So if you pick a capital stock in excess of the capital stock prevailing in the steady state C, the whole economy diverges. So the capital stock increases far beyond the point C, and we do not have global convergence to the point A, but only locally convergent behavior with this dynamic system C. Now the green line, for example, may help you to explain some phenomena in the field of economics, of development economics. So let's assume the green line characterizes a couple of developing countries. They all are in the rest point A, and the World Bank would like to decide how they should allocate funds. So should they target just a couple of individual countries, pick their favorites, or should they apply development aid equally to all countries? Now, if this is the situation in the developing countries, it would make sense to allocate funds to just a few countries so that their capital stock increases beyond point C and that they start to grow. If you, for example, only allocate little funds to all countries, for example, go from this steady state to this point here, they fall back and move back to point A, which we can also characterize as a development trap. Okay, so this model may be successfully applied also in development economics. For example, the shape of this curve may result from endogenous volatility, so that at this age perhaps we have, in this range, we have high volatility rates which even increase if we have higher income, and only for high income countries does the volatility rate, the population growth rate decline. This kind of behavior might result in a shape of the dynamics as presented by the green line on slide 22. How can instability in point C arise? Well, let's look at this more formally. We have the dynamics of the model characterized by the equation kt plus 1 is equal to g of kt, or when we substitute from our equilibrium condition of the model, savings divided by 1 plus n. And savings are a function of the wage W and the interest rate R, which, under the assumption of constant returns to scale, is a function of per capita production and the variable kt. Now this is an implicit equation of kt plus 1 in the equation kt, and we can form the total derivative to get dkt plus 1 over dkt and get this expression in the bottom line of slide 23. Now when you go back to our stable and unstable steady state here, you see C is unstable, C is stable. Well, you can't help noticing that A is stable because the slope of the green line is smaller than 1 in absolute value. And here C is unstable because the slope of the green line is larger than 1. So this is our stability condition, that the slope dkt plus 1 over dkt is smaller than 1. And now let's look when this is more likely to hold. So here we have let's look at the denominator. 1 plus the population growth rate n minus the partial derivatives of savings with respect to the interest rate, SR, times the second derivative of the production function with respect to capital. Now, this second derivative is negative because the marginal product of capital is declining with higher capital stock. We have assumed constant returns to scale and 2 production factors. So this term is negative, minus minus gives you a plus. So the denominator is getting smaller and this whole expression is getting larger if our partial derivative of the savings function with respect to the interest rate, SR, is smaller than 0. So if SR is smaller than 0, it's more likely that we have instability. Now, what's the intuition for this? So let's go back here to this graph of our dynamics. Let's assume we are on point C and we increase capital stock. As a consequence of higher capital stock, the interest rate declines. Now, if SR, the partial derivative of savings with respect to the interest rates, is negative, this means that our savings go up. So the income effect is so strong, higher than the substitution effect, that we increase our savings even though interest rate declines. If we increase our savings, however, then this will again increase the capital stock. And so this dynamic process continues and the capital stock is ever increasing. This is the intuition for this result, that we have local stability is more likely to fail if high interest rates reduce savings. Now let me already tell you that the model that we will consider in chapter 6 and in chapter 7 of the book will look at not only 2-period models, but of, let's say, 70-period models. So where each period is 1 year and people live 70 years. In this case, you will find out this condition is basically always met, that the system is stable. Within our 2-periods models, however, we have to check if local stability or if stability of the steady state prevails and is met the condition. Now in the following, we will look at a numerical example. So we will pick instantaneous utility function. Here we take the case that sigma is equal to 1, so that our intertemporal elasticity of substitution is equal to 1, which results in a logarithmic utility function. And we take the case of a production function that is equal to a Cobb-Douglas function, where alpha is the production elasticity of capital, 1 minus alpha is the production elasticity of labor, or equally the wage share or the interest rate share in total production. And we will derive the savings function, equation 20, and we will derive the capital market dynamics, our aggregate capital stock dynamics G of KT, and the steady state. And the characteristics of our little model will be the following. We will have a steady state, which is stable, and we look what happens if we take an initial capital stock. Well, we show that it nicely converges. So this will be the material of the next video tutorial, where we either use MATLAB or Gauss, as you like, to derive these dynamics and give you an introduction to the computer programs MATLAB or Gauss if you have not had prior knowledge of these programs. So I would advise you to get any of these programs, get the software, and then you might upload the next tutorial, which is a tutorial on the computer program OLG-Dyn1.m or G, depending on whether you use MATLAB or Gauss. And I would like to thank you for your attention and hope you also watch the next couple of tutorials.